Hello everyone, this is Ravit, and I'll be just showing you the next steps for part of the AITS DNNC project. So this next part of the project involves creating the actual implementation of the operators. And so I've created like a outline of a series of steps that you have to complete, one of each for every operator. So there are like 150 operators, and for each operator, we'll be following this series of steps. And I'll do a sample operator to show you how the whole workflow happens. And by the way, all the assignments are up here on the management page. I've assigned about everyone each 13 or 14 operators so that we can get them all done. And so hopefully, by the end of day, August 7th, will be you can show that you've at least started on one of them, and we'll see from there. So in this video, what I want to do is to show you how you can go about creating the implementation of each operator. So without further ado, let's begin. So here we start by cloning the repository. And so let's start here with this first step, create header file and include operators. For the sake of this demo, I'll be doing a rather simple operator, the add operator, which is very simple, very similar to an existing operator that's already implemented, matrix multiplication. So we'll be following that as a basis. For more advanced operators, such as convolution and etc., you may need to reference the Eigen documentation for more complex features. For add, it's relatively straightforward, as we'll discuss. Once you've cloned the repository, you can go to include operators. Here, you'll find that there's an existing header file, matml.h here. What we're going to do is we're going to create another header file, add.h. Here we will implement the compute function method in which we'll essentially just show what needs to be done with the input tensors, as well as catch any well, throw any errors if there are any incorrect parameters passed in. So start here and include operators. I'm going to open matml.h as well because from here we can make a few minor changes. Um, so here this needs to be add. And as for this operation name, you can find a full list in this base operator.h file. And so as you can see here, we're implementing op add here. In matml, that's the same thing here, op matml, which is right here. So that's where you can find the full list, and as of course, they're the full assignments on this project management page. So yep, here we're doing op add, and replace these two, no attributes right here. Um, Now this compute function is the bulk of the implementation. Essentially, this is the majority of the time you'll be spending is here implementing this compute. Now, what is this compute? Here it's essentially taking input of two tensors and returning the output. Obviously, for all operators, the number of inputs is variable, uh, and so you'd have to adjust accordingly. So in this example, what we can do is, since we already have existing code for matrix multiplication, we can make some modifications. For the add operator, we know that the shapes of the two input tensors need to be the same. If that is not the case, we can throw an error invalid argument, and instead of multiplication we can say add operator, tensor dimensions not appropriate for add operator. Okay, now we're going to create a new tensor for result with the dimensions of a shape. For this case, I know there are only two dimensions, and we're going to demonstrate this functionality for two dimensions. Of course, for the add operator, there need to be support for other dimensions, but for the sake of simplicity, let's keep it to 2. So here, this is where eigen comes in. You create this eigenmatrix A and my eigenmatrix B from the existing uh, inputs A and B, and here is where we get the result, the eigen result. Here in add, we can simply replace that asterisk with a plus sign. It's quite simple since the add operator is a very straightforward operation. As I mentioned, there are other operators that are more complex. Here you need to look at the eigen documentation. Then we load that into result and return result. And so that's pretty much it for add in the header file, and that concludes step 1 here. Step 2 is creating the test file .cpp in slash src slash operator. So let's go there. So here, as you can see, there's already an existing cpp file for matml. We'll create another one for add. You can go ahead and open those. Right. Similarly, we'll just use the majority of the code from matml, making some small adjustments here and there. So we have add. Let's replace this comment for consistency. Here we have the add operator. So we need to include the operator slash add.h, and this file is essentially has two tests, has a test here, creating two tensors. For the add operator, we need to ensure that they're the same shape. And there are two tensors here, A and B. Now instead of matml, of course, we have our add operation, compute the result of A and B, store that in result. And that's pretty much all the changes we need to make here. Um, you can make and go ahead and run this output. So first we need to compile and add a dash d for this if def. Oh, let's see, and run the output. And as you can see here, we get the output 2, 4, 6, 8, 10, 12. We've simply added two floats, element-wise addition of two float tensors of shape 2, 3. And so that was our test, and that is our CVP. We've created the CPP, we've also compiled and run it. So obviously this is a very simple example. For more complex operators, we'd be needing to create more rigorous and more test cases to ensure that the functionality of the operator in add.h is correct. If there is an error, you can go back to add.h and adjust it accordingly. Um, yep, and we're done with step 3 just like that. We've ran the output. Uh, Now we need to modify some Swig files. So Swig, as we mentioned earlier, is the interface between the C++ and Python, and this is so that we can have the same operators running on the Python. So this is in the Swig folder. Swig. Now we need to modify these DNNC.i and DNNC files. Now what we have to do, open this in the editor. Open these two. Okay, now we need to include add.h here, and we need to add another operation, another method for the add operation. So we can essentially just copy this code and make some changes since there's a lot of overlap. Takes as input two tensors, create an add operation, and return the output of the compute function when called upon this add operation. So then we move to DNNC.i. This is .i file is for Swig, the interface between C++ and Python. and we have to make a couple changes here. We need to add this for the add operator. Same up here. There you go. And at this point, looks like we can test it out. So make first, and let's see. So we first import DNNC. Okay, looks like that worked well. And cool. Now we looks like we have our DNNC.add method implemented using the steps. Let's go ahead and test it out. So we have let's create a new tensor from DNNC. DNNC.make tensor of shape 2, 2, right? Let's say 2, 2. And B is DNNC.make tensor 2, 2, right? There's an underscore here that is not visible on this terminal for some reason. Okay, and we have this, we can actually view the content, the values of this tensor, of the A and B tensors. So it's using this toString function we can see, toString. Similarly, we can do the same for B. These values are essentially arbitrary. And so now what we're going to do is to test this function dnnc.add. So dnnc.add A and B. And we can also similarly see the output c.toString. So these two are element-wise addition is carried out for each element in the vector, and the result is stored in C. C is also another tensor. Okay, now let's see what happens if we mess up uh, the shapes. So what should happen is that it should throw an error here, tensor dimensions not appropriate for add vector. So let's try that out. B is equal to make tensor of shape 2, 3, let's say, right? Okay, something went wrong. DNNC dot make tensor. Okay, now we have to look at the output. Let's say C's, or let's just say DNNC dot add AB. There we go. Value error, tensor dimensions not appropriate for add vector. So it looks like both the error and the whole functionality is working as expected, and we can go ahead and exit. At this point, we have finished the implementation of the add operator, and now that we're done, we can go ahead and create a pull request on GitHub here. As you can see here, you can generate a new pull request um, as you have the code for the add operator, and that should be it. So we have to continue this process for every single operator here. Once again, I've assigned everyone like about 13 or 14 operators. Hopefully we can all learn as we continue implementation of each operator. And of course, if you have any questions, you can go ahead and share it with the team, and we can all try and help each other out. And once again, this implementation was only done for rank 2 tensors, but it needs to be implemented for not only that, but also rank 1, rank 3, and rank 4, since that is the support for the add operator. And that's pretty much it. Let us know if you have questions, and thank you.